This video is the first truss problem that I gave you guys. I'm going to move my microphone over so hopefully it won't be too loud. So this is the picture. This is the one that you guys started in class actually. So we have this triangle. This is a 30, 60, 90 triangle, which is a special kind of triangle. I don't know. You guys are probably more familiar with this. It's been more recent for you than it is for me. But if we draw a straight line down here, we also have two similar triangles that are also 30, 60, 90 triangles. And so what's unique about this triangle is that the short side, which in our picture is B, is twice, that length of that leg is twice the length of the hypotenuse, which in our image here is C. So 2B equals C in this case. You can also, there's also a relationship between the long leg and the short leg. So the long leg is the √3 times the short leg. I don't know that that's useful in this application, but you can divide the big triangle into a medium triangle and a small triangle, and so they each have a there's a big triangle A and a medium triangle A and a small triangle A, and so you can see that some of the sides in the big triangle are also the sides on the medium triangle, also the sides on the small triangle. So what this really means is that if we look at this the hypotenuse of the big triangle down here, that if we go all the way to here, that's actually 3/4 of the length of this leg, of this hypotenuse, and then the remaining part is of course 1/4, which means we can set up a relationship that's just important so that when we set up our sum of our moments equals 0, we're going to choose a pivot point. And I think I chose this corner here, the AC angle. I don't like that they call those sides letters. I really prefer that the joints be labeled with letters. That's usually the way we do it, or that's the way I like to do it. But anyway, so this joint here, which is the angle between A and C, that's going to be my pivot point, which means that this downward force, the 100 Newton external applied force, is going to cause it to want to go clockwise. Sorry. And there's also a reactive force here at joint BC here, right? So there's an arrow that pushes up here. That arrow is going to make it go counterclockwise. And so there's a clockwise torque and a counterclockwise torque. The clockwise torque, and then when you sum those together, you get 0. So the clockwise torque is going to be 3/4, or 0.75 C times 100 newtons, right? Because torque is always the torque arm length times that force pushing down. So it's the force times the torque arm length, and that is going to be equal to the entire side, which is 1C, and the force F2, which is pushing up. So we know the sum of those two. Here's my moment conservation of moments here, right? So the sum of the two moments, clockwise and counterclockwise, equals 0, which means we can very easily solve for F2. F2 must be 75 newtons. And then we also know that the sum of the two vertical forces, or the sum of all the vertical forces, which are, there's this one pushing up at F1, there's this one pushing down, right, the external applied force, and then F2 is also pushing up. So if we know that the external applied force is 100 newtons, then that means, and that F2 is 75 newtons, that means that F1 must be 25 newtons. Now here the sign convention for forces is, because this is a y dimension, right? It's going down, that's a negative sign. And then these two arrows here, F1 and F2, point up, that's positive force. For external applied forces, the sign matters, I guess, a little bit. When we talk about the internal forces in each member, we're actually going to remove the signs. They're all going to be magnitudes, because we're just going to say if it's under tension or compression, and then the sign is irrelevant. Okay, so no, that last thing was F1, that was 25 newtons. So now when we figure out, the best way to really approach a structure is to look at each joint one at a time. So this joint, we're going to start with this one. And so the method of joint says that the condition for static determinacy, right, the sum of the moments is 0. And at this point, we're only going to be using the idea that the sum of the forces is 0, but you're going to look at x and y forces separately, and you're going to restrict yourself to one joint at a time. So it simplifies the problem. So if we just look at this green joint AC here, then we remember we have the external reactive force of 25 newtons that we just calculated in the first step. And we also have this member here and this member here. Now, the internal forces of these members is what we're about to calculate, and they have to be in the direction of the member, right? There's no other forces that these members there's no other direction other than the direction of the member. And so we know that the force of A is in this direction, and we know that the FC is in this direction, this horizontal one. So because FC is purely horizontal, this A member, FA, is the only part that has any vertical component that's going to counterbalance this 25 newtons. So that's going to be the first thing. We also know that it must go down, right? It has to be going down because it's the only way. A down arrow is the only thing that's going to counter this up arrow. So I already know that this arrow is facing this joint because it's the only way to negate this positive reactive force at the support. And then there's also an x component, which because the x and y components both go with this vector, which is going down and to the left, then the x component must be going to the left. Okay, let me know if that doesn't make sense. So we have an AY and an AX, and we know the angles because they are given in the problem. Now, FC is purely going in the x direction, xy direction, right? And so this one we're going to equate with the AX force. The two horizontal forces have to be equal. So we're going to start with the 25 Newton. The reactive force at the support plus AY must equal 0, which means that we know AY must be negative 25 newtons. Now in a minute we're not going to care about that negative sign. The negative just means it's facing down. So now if we want to calculate this vector, that's what we're asked for, is what is the FA vector. And so we know that FAY, which is this force here, sorry, I went from AY to FAY. I like to use F because it's a force. The problem asked for just A, but I'm going to probably, from the rest of the problem, call it FA. I apologize for changing. But FAY, the force at A, just the y component of that vector divided by FA, so that's here, is going to be equal to the sine of 30 degrees, right? And so that's because this AY, FAY is here, and the angle is here, and FAY is opposite, and FA is the hypotenuse. So we already know what FA is. It's 25. FAY is 25. So we just need to solve for FA using the sine of the angle, and that's going to be the magnitude of that vector. We also know that because we can also decide now at this point if it's under tension or compression. Now, I want to talk about that. I'm going to show you how to do that with these arrows, but we're also going to talk about it, try to rationalize it just from thinking about the problem in a minute as well. Okay, so we have these arrows. We know this one is pointing out toward the joint, and we did that because it has to negate this upward force, right? So we had to make it go that way. So in this member A, if this arrow is facing joint AC, then this member, the end of this member also has to have an arrow facing the other joint. Okay, so within this member, the internal forces, the arrows either face the joints or they face away from the joints. When they are facing out toward the joints, that's a sort of we have to think about the reactive force, right? So the actual internal member has these arrows reacting against that. And so you can see that these arrows face in, and that is compression. So whenever you're doing this, if the arrows face the joints, they point toward the joints, then that member is under compression because the internal force would be facing inward, which is sort of like it's squeezing in, like compression. So the answer, to summarize this first member, FA equals 80 newtons, and it's under compression. Now, you can often identify tension or compression just from looking at the problem, and I want to do that next. Okay, so sometimes when I do these problems, I like to start by thinking about tension and compression in the beginning. So let's do that. Let's do this little tiny triangle. This is just a representation of the same triangle. Now, in this case, I'm gonna draw my little triangle, and I'm thinking about this force down. So if this force down is this red arrow, and this is a little smaller triangle. And what I'm going to do is I'm going to pull down, and I'm going to imagine what would happen to this triangle, this structure, if I remove one member at a time. We talked about this a little bit in class, right? So if I pull down in the place where the force is pulling down, let's say I remove this member where I put this blue X. If I remove this member, then I can envision that as I pull down, what's going to happen is this member here is just going to collapse, right? And it's just going to fall down onto itself. And so because I can envision it collapsing, I know that this member must be under compression. So I don't know if that makes sense to you. So I like to try to think about which one's tension, which one's compression at the beginning. But then at the end, you can always use the arrows, right? If the arrows face the joints, that means that those are reactive arrows that the true internal forces face in, which is compression. Let's keep going and think about the other members under tension and compression. So let's redraw our small triangle and remove a different member and see if we get an agreement. So now we have this and we have our force pushing down that I'm going to redraw here as a red arrow. Let's remove this member. Now I can envision that if I did this, the same thing would happen. I think that this member up here would fall, and so since it collapses, I can imagine that this member must be under compression because this guy's pushing down on him. Right, so I think that this member B is under compression. And then this last member is likely under tension. You know, usually you have some tension members too. And I think that makes sense. If I push down, we're probably stretching this guy out. But if we remove it, then I think what's going to happen is it's just going to kind of fall down and go splat, right, like that. And so if that's true, that means that this member is being pulled out. And that's the only reason it's not going splat is because it's still there, but it's being pulled on. So that's a tension member. So C is under tension. But we'll verify that when we finish the calculation. So let's move on and do another side. Okay, so we're looking at joint AC. We could figure out C at this point, but it looks like I'm moved on to joint AB in my cartoon here. So I remember that this arrow is facing, this arrow, A, is facing this joint. And we decided that because it has to be because we decided down here this A is facing this joint AC. So it must be the whole member is under compression. So we already know the direction of this arrow, we already know the direction of this arrow, and then the only other member is B. And so if we draw the force for B, then we have to draw it in this direction. Okay, and the reason for that is because there are only two forces here that have horizontal components. A has a horizontal component and B has a horizontal component. This external force is only vertical, which means that this A and B have to be facing each other, otherwise they would not cancel out, right? Otherwise it would not be static. And so because these two must cancel out, they must be facing each other. And that's what that's saying, is that the horizontal forces along X are equal, or they sum to 0. So the sum of the forces along X must equal 0, which means FAX, right? That's the horizontal component of FA, plus FBX, the horizontal component of FB, must sum to be 0, right? So they face each other. And I drew this one in blue, which is why I'm changing this color to blue, just to keep it straight. Okay, now, if we redraw our A vector, and we know that FAX is what we care about, earlier we calculated FAY, so if we want to calculate FAX just so that we can figure out what FBX is, so that we can then figure out what B is, next we need to calculate FAX from FA, right? So FAX, which is here, right, or if you think about it up here, wherever you want to think about it, FAX is the adjacent to this 30-degree angle, and then the hypotenuse is here. Of course, that's FA, and we just calculated that in the last step. So FAX adjacent divided by the hypotenuse FA equals the cosine of 30 degrees. So if we solve for that, we know that FAX is 43.3 newtons, and that is the same as FBX. So that's the horizontal component here. They are equal because they have to cancel out, right? So now we know that FBX is 43.3 newtons, which means we can solve for FB. So FBX here, right, is the adjacent, and then of course FB is the hypotenuse, and now our new angle is 60 degrees over here. So FBX, the adjacent, divided by FB, the hypotenuse, is equal to the cosine of 60 degrees. And so this is also that we can calculate what is FB, right? The force within member B. So that's that angle there. So And whether you think about it down here, whether you think about it this little tiny triangle, whatever you want to think about, that means that FB is equal to 43.3 divided by the cosine of 60, which is 86.6 newtons. Now, when we think about tension and compression, right, we have an arrow. I'm just rewriting the answer, newtons. So we think about tension and compression. We already sort of decided that this member was under compression, right? We did that at the beginning, but we should verify that with our little arrows here. So again, this green arrow is pointing toward the joint, which means that this member must be under compression because this is toward the joint. The internal force within the member is going to face the other direction, right? So the internal force within the member faces the other direction. And so if I draw the member here, then it is clearly under compression. So remember, the arrows face the joint, they point toward the joint, then that is a compression member. And that matches what we decided earlier anyway, so I feel pretty good about it. Now let's look at C. I'm going to redraw our 100 newtons. We could figure out C from either of the other two pieces of information we already have. We could have actually done C earlier when we were doing joint AC, but we didn't. So now we know, let's draw the forces at just this joint down here, okay? So here, so now we know that there's this force here, this upward force is our reactive support force that we figured out in the very first step. And then we have the two members here, C and B, and those are the only three that come together here. So we need to decompose this member, B, into its X and Y components. This member, C, is only horizontal. It doesn't have any vertical component at all. So the sum of the forces along X is 0. The sum of the forces along Y is 0. So along X, all we have is FBX, which is the X component of FB, this arrow here. And then FC is purely horizontal. There's no vertical component. So if you sum FBX and FC, you should get 0. You can also use the vertical components to do the same thing. We could have used joint A. That's what I was just saying a minute ago. So that's what I'm drawing over here, is that we could use FA. We could say FAX equals plus FC equals 0 as well. I don't think we calculated FAX in step 1. Maybe we did. If you already have it, then that would save you time. Maybe we did. So here, looks like I used FAX, but you could easily calculate FBX as well. And either way, you should get 43.3 newtons is FC. Now, if we're deciding tension or compression, we've already looked at this. We already think this member is under tension because you pull down and this gets stretched out, right? But the arrows also indicate that, right? So this arrow is going away. The arrow at joint BC is facing inward. It's pointing away from the joint. We made it face that way because we know that this arrow faces toward the joint, and these are the only two horizontal components. And so because this one faces to the right, this one has to face to the left in order for them to cancel out. We also would have done that over here. This arrow would have faced toward the joint, which means this arrow has to face away from the joint in order for the X's to cancel out. So that means that the arrows face away from the joint, which means the internal forces in the member face out, which is tension, right? So this member is under tension. We've already figured that out. We did that in the first step, but I'm going to write T here in parentheses, which is kind of the standard format for if you write under tension or compression. So I think I'm just erasing this so I can summarize. We have the force at A, the force at B, tension and compression, and we have F1 and F2.